I started the recording.
Welcome to today's tutorial of our Stochastic Programming Society seminar series. I'm particularly pleased today to introduce our guest speaker, who is Francesca Maggioni, Professor Francesca Maggioni from University of Bergamo. She is now currently in the Department of Management, Information and Production Engineering, but we were until a few years ago colleagues in a different department before I moved to Halifax University, and then she moved to the Department of Production Engineering. So Francesca is a very, very active colleague. That is particularly I get to know her since 2006 when she moved to the University of Bergamo. And then we collaborated with Professor Marida Bertocchi in the department of at the time, Department of Mathematics. And then we were co-organizers of the International Conference on Stochastic Programming that took place in 2013. So I would like to just mention that Francesca is currently the chair of the Euro Working Group on Stochastic Optimization, which is the Euro-based Stochastic Programming Society. But she's also, not everybody knows this, she's also chair of the Italian section of the Stochastic Programming Society for the Italian Operations Research Society, and which is a position I took in the first place, and then she followed me, so I'm very, very pleased of that. And then in terms of scientific contributions, more recently, through time, she's been contributing with several very effective approximation methods based on upper and lower bounds from stochastic programming, classical stochastic programming problems initially, then into multi-stage stochastic programming, and then increasingly also providing very effective and flexible approximation methods for more complex problems, also in distribution robust optimization, and more recently with stochastic dominance characterization. So we have been co-authoring several papers, and she has been collaborating with colleagues from the community. My memory goes back to Marida Bertocchi, surely, but then Georg Flug, then more recently with Andrei Rozhinsky and Darinka Dencheva, and we've been working with them together. So I don't think she needs far more words by me. She will be presenting today. It is a tutorial, but then she will be presenting some more recent results on bounding methods for multi-stage optimization problems under uncertainty, formulated in several different ways. So thanks a lot, Francesca, for accepting our invitation and be part of this celebrated Stochastic Programming Seminar Series. So I leave you.
Thank you very much, Giorgio, and thanks a lot for the kind introduction and for the invitation. It's really a great honor and pleasure for me to be here and to be part of this important event of the Stochastic Programming Society. So in this tutorial, I will talk about bounding multi-stage optimization problems under uncertainty. I will start with a brief introduction about stochastic programming in this tutorial, and then in the last part of the talk, I will describe some more recent bounding techniques for multi-stage optimization problem under uncertainty. So in a real life decision problem, in different contexts from finance, pension funds, insurance, production, transportation and logistics, energy, we needed to cope with problems which are, first of all, dynamic, which means that we needed to take a sequence of decision over time. And in between each time in which we needed to take this sequence of decision, some random parameter can affect our problem. So in other words, our problem very difficult because they are affected by uncertainty. And among the possible solution frameworks that are able to cope with such a kind of uncertainty, there is a stochastic optimization, robust optimization, and distribution robust optimization. So if we just describe our problem as a minimization type of problem where we wanted to minimize a certain objective function where x is our decision variable and psi represent our parameter or data, in the case of deterministic optimization, we assume to know completely our data. So we have a full knowledge about the values of our data. While in the case of stochastic optimization, we assume to have some information about the probability distribution. So suppose, for instance, to have some historical data. And so we can extrapolate from this historical data the probability distribution or the probability distribution of them, and then solve the optimization problem, which can be expressed like this. So we minimize the expected value over all possible realization of the uncertainty, which is distributed according to the probability distribution P. However, in some contexts, unfortunately, we don't have so many data. So if we don't have so many information, we can adapt a much more conservative approach where we can assume to have information just about the support of our uncertainty. And so some possible characterization of support could be given, for instance, as a box or ellipsoidal or spherical or polyhedral representation. And so a min-max type of problem can be formulated. In between these two approaches, so in the case we don't have such detailed information about the probability distribution, a much more recent framework which has been developed and is very now well known in our communities, the distributional robust optimization setting, where we still want to minimize in the worst case, but by assuming that our probability distribution now belongs to a certain ambiguity set, which means that we want to optimize in the worst possible probability distribution, which belongs to a so-called ambiguity set. So I will focus to some approximation techniques in this very general setting. However, it happened that such a kind of problem from a computational perspective forms a class of extremely challenging problems. Here, for example, we can see a scenario tree representation of a multi-stage stochastic optimization problem, which allow us to describe stage after stage the description of our uncertainty. So typically when we model our problem through this scenario tree, the problem becomes bigger and bigger because we needed to duplicate the decision variable and constraints stage after stage. So it can happen that at a certain point, our model becomes intractable and our computer goes out of memory. And so in this kind of context, approximation techniques which provide a lower and upper bound to the optimal value of the original stochastic optimization or robust optimization or distributionally robust optimization are especially important. So I will now start in providing and proposing some types of bounds and approximation which have been proposed in the literature, starting with the two-stage case and then moving to the multi-stage case. So I will try to answer to the following 4 questions. The first one is how to bound a two-stage stochastic program via functional and distributional approximation. The second one is to bound a multi-stage stochastic program via the concept of stochastic dominance. The third one is how to bound a multi-stage stochastic program using the concept of scenario grouping. So by dissecting the scenario tree into some smaller groups. And finally, how to apply the same idea of scenario grouping in the context of distributionally robust optimization. So as I said, where we don't have a specific knowledge about the probability distribution, which represent the uncertain parameter of our problem. So I will structure the presentation going through the details of these 4 types of possible bounded approximation. So I will in particular present the numerical results on a very simple multi-stage mixed integer stochastic programming problem, then extended to distribution robust optimization for inventory management. More detail will come later. So let's start with the first. So how to bound a two-stage stochastic optimization problem using the concept of functional approximation or distributional approximation. So first of all, recall what we mean for a two-stage stochastic linear program with fixed recourse. We are going to minimize a certain cost function, C transport X. So this represents the cost that I will pay at the first stage before of the realization of a random event. The random event will be described through a random variable xi, which is distributed according to a probability distribution P. And then, after the realization of this random event, a second stage recurse action can be taken, which depends by what I decided before and also by the realization of our uncertainty xi. So in order to take into account about the cost that we need to that we have by facing this two-stage sequence of decision, the classical implicit representation of a two-stage stochastic program is as follows, where we can see that the second stage value function Q of X is actually the expectation following the probability distribution of a certain cost Q of X xi. However, the expectation actually is the integral over the support of our probability distribution of a certain cost Q, which is described by some constraints which link the first stage with the second stage decision. So we can easily understand that the main problem that we have when we want to solve this kind of problem is the computation of this integral, because typically when we solve our real-life decision problem, actually the decision variable X belongs to a very high dimensional space as well our uncertainty xi. And so typically the computation of this integral is not possible to be found. So we cannot find an analytical expression in a closed form of this integral. So the idea that many authors in the literature had was then to approximate for a given first stage solution x0 this integral by means of functional approximation or distributional approximation. So in other words, in the following, what I will do is to represent our second stage cost function for a specific decision x0 by a certain function f, and then provide some bounds which approximate this integral. As I said, for most of the function f, this is not possible to do exactly. So the idea that functional approximation is to find simpler function u for upper bound and L for all lower bound, which approximate the original expectation from above, from below, and whose expectations are easily evaluated. So in other words, we are approximating the integrand function. So for example, here we can see a piecewise linear approximation which approximates from above a certain quadratic function. The other kind of approximation is, on the other hand, working on P, on the probability P. So instead of approximating the integrand function f, we approximate the probability P. And so we want to find an alternative distribution, let's call it Z, whose evaluation of the expectation give a bound. And typically, as we will see, if we move the probability to some certain point, to some, for example, some barycentric points, this will provide some lower bounds, while if we move our probabilities to some extremal points, will provide some upper bounds. However, as we will see, these two approaches are tightly connected since they are linked through strong duality, and they represent the so-called generalized moment problem. Several are the contributions which has been proposed in the literature. We can see that the bounds based on functional approximation are from the so-called Jensen inequality, Madansky inequality, some bounds by Wallace, Burge, Morton, and Wood, etc. Other one based on distributional approximation are here listed. As you can see, some of the bounds can be considered as both a functional and distributional approximation according to the generalized moment problem interpretation. And more recently, another class of bounds has been proposed and is based on the concept of a scenario tree decomposition via group subproblems, and they originated from the seminal work of Burge of 1992. So I will start now by describing a little bit on how the distributional approximation work. So the idea, as I said, is to find an alternative distribution, which is simpler. And actually, instead of computing the expectation over the original probability P, compute the expectation using this new probability distribution Z. So the upper bound will be obtained by maximizing over Z inside a certain set, while the lower bound will be obtained just by minimizing the same expectation over Z. So the set which describes the possible probability distribution is as follows. So we require that the support of our probability Z is the same of the original P with Xi convex and compact, and then we impose some generalized moments. So we describe a priori, we decide a priori how many moments we wanted to include. And this will be done through some generalized moment function GI, which are easy to be handled. And the interesting fact is that the contribution on different bounds in the literature lie, of course, in the different choice of this generalized moment function. However, it's interesting to see that even if the support of the original distribution was continuous, the optimal approximating distribution, denoted here by Z asterisk, actually is all the time discrete. And it is composed by at most capital I plus one point, where capital I is the cardinality of moments which we impose. So several are the contributions which belong to this kind of solution method, from Jensen and Madansky inequality, Freudorfer, Cole, Burge and Wetz, etc. And we see that the main difference among them is about the type of bound, lower and upper bound, and the type of a generalized moment function which has been used. And so, of course, they provide some different probability with a cardinality of the support which can vary. More details are reported in this review recently appeared in ITOR in 2023. On the other hand, functional approximation can be obtained in the following way. Instead of discretizing or simplifying the probability distribution, now we wanted to simplify the function, the integrand function f, through some function that we denote here by L or U, L for lower bound, U for upper bound, which are actually given by an affine combination of our generalized moments. And so in this sense, we need now to identify the optimal weights Ui, which describe our function. In other words, a lower bound can be obtained by maximizing the expectation of the function L, such that L is a lower bound to the original function and the upper bound just minimizing. Interestingly, as I said, the function approximation is connected with the distribution approximation through the strong duality. In fact, if you see, here we have a capital I plus one decision variable, while in the previous case we have capital Y, I plus one constraints. And here we have an infinite number of constraints, while in the previous case we have an infinite number of decision variables. So these are semi-infinite optimization problems. For example, let's now see how to apply it on a very simple case. We suppose to have a one-dimensional uniform distribution defined on the support 0, 1. and having mean equal to 0.5. The objective function is given by xi to the power 4, and we consider as moment function gi given by xi to the power I, and to consider the moment 0, 1, and 2. Then we can see that on the left-hand side, we have three type of a function which approximate the original function f from below. The first one is just by considering the moment 0. The second one, L1, considering moment 0 and 1, and the second one considering the 3 moments. And the supports of the approximating distribution actually, as you see here, are discrete. So if we consider the first moment, the xi with I equal to 0, we obtain that the support is just given by 0. If we consider the first one, we obtain 1/2, and then the other one 0 and 2/3. So as we see, we obtain some distribution which are discrete and which are located on some finite values, even if the original support was continuous. And similarly, we can do for upper bounds. So by solving the problems that I discussed before, we can obtain upper bounds by considering an increasing number of moments. So two of the very well-known bounds, like the Jensen lower bounds and the Edum-Madansky inequality, can be interpreted according to the generalized moment problem. And in fact, we can see that the Jensen inequality, which says that if we have a complex function over the support of a random variable, then the expectation of it is greater or equal of the function of the expectation. And so we can interpret the Jensen inequality according to this interpretation. The same happened also for the Edum-Madansky upper bound. For example, we can interpret it as a function approximation where we substitute the integrand with this function u. The function u is just given by this line, and this line actually will be substituted inside our integral. And actually, by making some computation, we can see that these correspond with the line having extremal points A and B, which are the extremes of our support where our function was defined. And so also the Edum-Madansky inequality can be interpreted as a function approximation, but also as a distribution approximation. Distribution approximation by putting the weights on the two extremal points, function approximation by substituting the function with this line connecting the two extremal points. So after this introduction on the bounds, which has been proposed in the literature on the two-stage case, now I will pass to the multi-stage case. In this case, as we know, instead of having just two decisions, X and Y, we have to take a sequence of decisions over time, making the problem much more challenging from a computational point of view. In terms of notation, I will represent with the letter x0 and xt, the different decisions over the stages. By xi, we represent our random process, and the history of a process up to time t will be denoted with an apex on the top. So we are now trying to provide some lower and upper bounds to this kind of nested formulation of a multi-stage stochastic optimization problem. Going to the literature, most of the bounds in the multi-stage case are based on a distributional approximation. Most of them refer to the risk-neutral case, and they can be broadly classified as barycentric bounds. These are mainly based on the contribution of Fraudorfer, Kuhn, Schurl. Moment-based approximation by Edelsinger and Zimba. Stage aggregation and discretization by Daniel Kuhn. Sequence of subfiltration by Casey and Sen. More recently, we have proposed another type of bounds based on distributional approximation based on the concept of stochastic dominance that I will briefly describe later. And these can be also applied to the risk-averse case. So, with respect to the literature, which was most on the risk neutral, we now propose a method which works also for the risk-averse case. Another class of bounds, which is more recent, is based on the extension of the scenario grouping idea, which has been, as I said, proposed by Burge in 1992, and most of them refer to the risk neutral. More recently, some contribution have been proposed also to the risk-averse case, multi-horizon, and the standard quadratic optimization problems. So I will now try to answer to the second question. So we try to bound in the multi-stage setting optimization problems affected by uncertainty using the concept of stochastic dominance. So let's try, first of all, to recall what we mean for stochastic dominance. Supposed to have a two probability distribution, P and P tilde, defined on a certain support R to the power M. We say that P is dominated by P tilde according to the first order sense if, for all non-decreasing integrable real value function f, the integral over P is less or equal of the integral of f over P tilde. Okay, so in other words, we can see that there is an analogy with respect to what we have seen before, because this f of u is our integrand function that we would like to approximate, and so the idea on which we have based the construction of these bounds based on the stochastic dominant principle is to construct a new probability distribution P tilde, which can be easier and it can be discrete instead of continuous, and which provided by construction, in the case the integrand function satisfies some properties like to be non-decreasing and integrable, so provide an upper bound to the original cost function. The definition of convex order stochastic dominance is the same as before, but we require that the integrand function now is convex and integrable. This kind of relation is also very well known in the literature as Lorentz dominance or Bishot-Delot ordering. So this is the definition, the classical definition in the static case. Of course, if we wanted to extend the definition in a multi-stage setting, we needed to be very careful due to the fact that there are conditional distribution, and so we needed to take care about that. I will not enter into the detail. However, in this work done in collaboration with Professor Georg Flug, we propose an extension and a creation of some bounds based on this context, based on these concepts, in a multi-stage setting. So for the sake of illustration, I will just present the idea on a three-stage problem. And we suppose that our uncertainty is described according to this continuous probability distribution. Here I just represent 1,000 sample, which where Xi1 represents the uncertainty in the first period, while Xi2 is the uncertainty in the second period. So the idea is then to dissect this support of our joint probability distribution into some rectangles, and then put the weights of a probability distribution on some points. For instance, we put all the weights of this rectangle in the right and upper corner, and we do the same for all the other one. In this way, as you see, we have only 6 points, and we can organize this 6 points into a scenario tree, which is a three-stage scenario tree, with 3 branches in the first period, which correspond to the 3 values we can observe for Xi1, and then conditional to the value in Xi1, we have 2 values in Xi2, which actually are the values that we obtain in the second period. So in other words, what we obtain according to this first order stochastic dominance construction extended to the multi-stage case, we obtain a finite scenario tree which allow us to obtain a finite probability distribution which dominate the original one according to the first order stochastic dominance. Similarly, if we put all the weights on the left and down corner, we obtain a new probability distribution which is discrete and which is dominated by the original one according to the first order stochastic dominance sense. However, from a computational perspective, it is very easy to be implemented because we obtain from these values a scenario tree structure. So going back to our multi-stage optimization problem, we need now to assume that our cost function is monotonic in the uncertainty and in X. And so if we substitute P tilde up with this scenario 3 and P tilde down with this other, we obtain respectively an upper and a lower bound to the original multi-stage stochastic program. Of course, much better bounds can be obtained by considering more information about the probability distribution. And this actually is like an extension of the idea of the Edum-Madansky inequality to get upper bound and Jensen inequality to get a lower bound. Suppose again to start with a continuous probability distribution over this support, Xi1 uncertainty in the first period, Xi2 in the second period. We dissect the support into some rectangles, and now instead of putting on some corner on the down and left or up and right, we consider the weights which are on the extremal points. While to get lower bounds, we put all the weights in some barycenters which appear in all the sub-rectangles. So according to this construction, then we get a finite scenario 3, which actually, as we see, is composed by as many branches in the first period according to the number of points that we dissect our uncertainty in the first period, and then conditional to each of these values, we have 4 values in the second period. Similarly here, where we just count actually the number of barycenters in the first period and then conditional in the second one. So here, of course, we needed to remember the hypothesis since we are working with the convex dominance. So the objective function, the cost function Q should be convex in the uncertainty. And in the case Xi2 is independent by Xi1, then we get, by implementing a scenario 3 structure like this, an upper bound, while if we implement a scenario structure like this, a lower bound. The condition of independence actually can be easily relaxed, and so we needed to subtract a correction term. I will not enter into the detail, but just to tell you that we can manage both the dependent and independent scales. Here, for the sake of simplicity, as I said, I presented to the 3-stage case, but it can generalize to much higher number of stages. In terms of application, I will just now present a multi-stage mixed integer production problem that we have used as a toy example for testing our bounds. For the sake of time, we will not enter inside of a mathematical description of the objective function and constraints, but just give the general idea of the problem. We have an inventory management that needed to meet a random demand, which occur in a certain number of period, for instance, in a week. And so our producer needs to decide the quantity that he needs to produce every day, and the quantity that he needs to put inside the inventory. And in order to meet the uncertain demand, he can also buy from external sources at a higher price. So this is the problem that we had to consider from a mathematical perspective, was a mixed integer and multi-stage production problem. Let's consider now the case in which the distribution P is given according to these two assumptions. So we, in other words, assume that the uncertainty are continuous in the first period and also in the second period. In the second period, we have a dependence with respect to the first one. And so, I mean, by purpose, we decided to assume some continuous distribution in both the periods, and we consider a 3-stage case. And so the idea was to try now to approximate this continuous distribution according to the concept of stochastic dominance presented before, providing upper and lower bound. And these are the results in the case of the first order stochastic dominance. This number that you can see are the number of branches in each of the period. So for instance, here we are considering a scenario 3 composed by 25 scenarios, 5 in the first period and 5 in each node of the second period. And so we can see that at the beginning, with a scenario tree composed just by 25 scenarios, we have a difference between upper and lower bound that is quite large, 140 units, but by increasing the cardinality of the branches of the scenario trees, we get actually very good values in terms of upper and lower bounds, because the difference is just a few units. Here is in the case, actually we have implemented a risk-averse version with average risk in the objective function, and this was the case of alpha equal to 0. However, other results that are very similar to this one are obtained also for other values of parameters. What happens if we consider, on the other hand, convex stochastic dominance? The results are much better, of course, but this was very intuitive, since we use more information about the distribution. So we don't put the weights just on one corner or another one, but we use the information of the extremal points and the barycenters. And so we can see that now with a scenario tree with just 400 scenarios, we close the gap. So the difference between the upper and the lower bound is equal to 0. Okay, now I will try to answer to the third question. So another type of another type of bounding approach, which has been proposed in the literature, is based on the concept of scenario grouping. So in this case, the main assumption is that the random process has finitely many possible realizations. This means that we start with a sufficiently large scenario tree, which describes our uncertain parameters. However, it is so big that our computer, unfortunately, is not able to solve it. So the idea of scenario grouping is very simple and very intuitive, and is obtained by splitting the original scenario tree into some subgroups, subproblems, and then combine the objective function value of all of these subproblems in order to obtain a lower bound to the original multistage stochastic optimization problem. Of course, here we are approximating the problem, which is already an approximation, because we start under the assumption that, as I said, a sufficiently large scenario tree is given. However, from a computational perspective, it is very useful, since we can be able to solve and provide bounds to problems which actually are not solvable. Putting a little bit of notation and mathematics, the idea is that we split the support of our uncertainty with associated probability distribution into some subgroups. We can decide to have subgroups with all the same cardinality, or they can also vary among them. And we assign to each of these subgroups a new probability distribution. In order to obtain a monotonic chain of lower bounds, we need to construct the probability distribution at a certain level J as convex combination of a probability distribution of a more refined level. And then a lower bound to the original program can be obtained just by combining the objective function value of all of these subproblems. In this way, it can be proven that a monotonic chain of lower bound can be obtained with respect to the original multistage stochastic optimization problem. We can provide this kind of lower bounds in different ways. By considering disjoint partition, this means that all the subproblems are independent, one from the other one, and they do not share any scenario. And one very simple chain of lower bound associated to this representation is here reported, supposed to have a scenario tree composed just by 8 scenarios. Then, if you solve them, all of them independently, we are just solving the so-called wait-and-see problem. If we combine pair of them, we obtain the pair subproblem. If we combine pair of these pair subproblem, we obtain this kind of subgroups composed by 4 scenarios. And if we make the union of them, we obtain the original scenario tree. And so, by following this kind of construction, we can obtain a monotonic chain of lower bounds. Of course, we needed to redefine the probabilities and the weights of all of these groups, which we split the scenario tree. But we can also decide to share some common or reference scenario among all the subgroups, because, for instance, the expert opinion tell us that that is a very important recurrent scenario. So we can decide to keep, for example, the scenario number 1 fixed in all the subgroups. And so we can easily find another type of chain of lower bounds where we start with V2 and then V3 and then V5 and then the original multistage stochastic optimization problem, where this number 2, 3, and 5 now are associated actually to the cardinality of each of these subgroups. Again, also here we needed to redefine the probabilities of the subgroups and the weights according to some rules that satisfy the property described above. In terms of numerical results, we test also this kind of bounds on the same multistage mixed integer production problem that I presented before for the stochastic dominance construction. In this case, we consider a 10-stage scenario tree with this kind of structure. My computer was not able to solve this problem with such a large number of scenarios. And so we decided to apply this bounding approach based on splitting the domain of the scenario tree. And we can see that we have a better and better lower bounds, of course, at expenses of a larger CPU sequence. And the best lower bound that we obtained was just obtained by splitting into the original scenario tree. So you can see the number that is here represented or reported is the cardinality of each of the 2 subgroups in which we split the original scenario tree. The difference between the best upper bound and the lower bound was 2.79% of the best lower bound, where the best upper bound was just the expectation of expected value, which is obtained by fixing the solution coming from the deterministic or expected value problem up to the stage number 8. So, of course, these are 2 different types of bound. The first one can be used in the case we have also a continuous distribution. Here we needed to start with a sufficiently large scenario tree description of our uncertainty. Now I will come to our last question: how to apply this idea of scenario grouping in the context of multistage distribution robust optimization. As I said before, in the case of multistage distribution robust optimization, we don't have a full knowledge about the probability distribution, about which represent our uncertainty, but we know that our uncertainty will be described by a problem like this. So in other words, we wanted to find the best solution in the worst possible realization of the probability which belong to a so-called conditional ambiguity set. Conditional because this ambiguity set will depend by the uncertainty of the previous stages. And so here we have a nested formulation which is very similar to what happened to stochastic programming, but we need to add this term here in blue just to take into account this min-max. What we mean for conditional ambiguity set? The conditional ambiguity set is the set of probability distribution at time t or a period t condition to the history up to t-1, which belong to a certain set of probability distribution on a support xit, such that the distance between this new probability and the nominal one is less or equal than a certain radius rho t. So this means that if we consider our original scenario tree, which we are typically using in stochastic programming, now the idea is to construct in each period like a conditional ambiguity set. In the first period, we will have a class of probability distribution, which has as nominal one, the one here represented with these 4 scenarios. And then in the second period, conditional to the node 2, we will have this other type of ambiguity set and so on. Several are the ways which are available in the literature, and the literature is very rich on how constructing these ambiguity sets, mainly based on moment-based, phi divergences, Wasserstein distance. in a work that we did in collaboration with our dear friends and colleague Guzin Bayraksan and two of our former PhD students, Daniel Faccini and Arthur Young, was to consider as a description of a conditional ambiguity set, phi divergences and Wasserstein distance. And so in order to construct in such a context lower bounds based on the idea of scenario grouping, we proposed these two criteria. The first criteria that we call first level criteria works as follows. So suppose that we have our original DRO problem, where since now we are in a DRO context, we have also to fix in each period a radius. So rho 1 represents the radius of the ambiguity set in the first period, and then rho 2 represents the radius in the second period. So instead of solving this big problem, assume that we are not able to solve, the idea was to split it into some independent subproblems. They can also share some common or reference scenarios, as we did in stochastic programming. And then, of course, since these subproblems are also DRO problem, we needed to fix for all of them some other ready of ambiguity in the first period and in the second period. So in all the periods. We solved them, and then we needed to combine this objective function value of all of the subproblems by solving a new DRO problem where we needed to fix another level of ambiguity rho bar bar. So what we call first level criteria was obtained just by splitting into some DRO problem which are smaller and then solving a new DRO problem in order to find a lower bound to the original one. So we can see that we had to introduce many new free parameters because we have many ready, each of them associated to each of the groups, and also a new radius rho bar bar associating on how to combine the objective function value of all the subgroups. And so the main question that we had to answer was, what is the relation that this ready and rho bar bar should satisfy with respect to the original ready in order to obtain a lower bound to the original problem? So this was the first method. Then we also proposed a second method which was more involved and that we call a multi-level criteria, where instead of combining just in one step all the objective function values of the subproblems, we combine them in a nested way. So in other words, we, for instance, consider the first two subproblems, we solve them, and we obtain a lower bound, Z14. We do the same for the other two subproblems, we obtain a lower bound, and then we combine these two objective function values in order to obtain a lower bound to the original 8 scenarios the rho problem. So, of course, in order to ensure that the objective function value that we obtain using the first level and multi-level criteria are related to, in order to obtain a lower bound to the original problem, are related to the choice of a measure of distance, by divergence of Wasserstein distance, and also by the choice of this parameter with respect to the original parameter. And the answers were given by these two theorems. The first theorem apply only to the phi divergence case and apply using the so-called first level criteria. And we obtain, according to the different type of phi divergence, a condition that should be satisfied among the ready of all the subgroups and the ready of the original big DRO problem. Theorem 2 is actually a similar theorem, but hold true both for the Wasserstein distance and also phi divergence. And again, we can see the conditions that are sufficient to be satisfied in order to obtain a lower bound to the original DRO problem. In terms of, very briefly, some numerical experiments, these are lower bounds that we obtain for the mixed integer production problem, which has been formulated in a DRO version using a modified chi-square distance. And we can see for increasing CPU time, the objective function value that become larger and larger by increasing the cardinality of the scenario for different combination of Robar bar and Robar max, where Robar max is the maximum of a ready among all the subgroups, and we can see that the monotonic chains are respected. In this case, we were not able to solve the full zero problem, and so we can just evaluate the difference between the best upper bound and the best lower bound that was of the order of 2.98% of the best lower bound. Similar, we got results in the case of the multi-level lower bounding techniques for the assistant distance case. And again, I will not enter inside the detail, but you can see that by increasing the cardinality of each of the subgroups allow us to obtain better results. And by, in the case we have a very small subgroups, just with L equal to 1, it is more convenient to put more weight to the second level of the ready, so to the so-called Robar bar, instead of the ready of the subgroups. So I'm now arrived to the end of my talk. So in this tutorial, easy to compute bounds for two-stage and multi-stage stochastic optimization and distribution robust optimization problem have been described. For stochastic optimization, I proposed bounds based on distributional approximation, function approximation, and on the concept of scenario tree decomposition via group subproblems. While in the zero context, we have obtained conditions to ensure lower bounds based on the risk parameters. The general take-out message is that this kind of bounds are very general, because they don't require any structural properties, and so they are applicable to a broader class of problems. Of course, the research is still ongoing and is in progress. Potential future research direction where the community, and I mean, I'm also trying to work with some students and colleagues, is to provide the bounds for multi-horizon stochastic optimization and distribution robust optimization problem, or it's possible to integrate some of these bounds with decomposition techniques like progressive edging, Bender decomposition, in order to speed up the solution of the algorithm, or provide bounds for other type of problem, like the decision-dependent optimization problem or contextual stochastic optimization, and many others. So with this, I thank you again. So here there are some references. Of course, I will be available to further discuss and to provide all the material of this talk. Thanks a lot.
Thank you, Francesca. Thank you. And